and welcome to episode number 18 of CS350 Online. I'm your host, as always, Leslie Eisted. In today's episode, we are going to return to the wonderful world of I/O and devices. And if you've forgotten all about it, don't worry. We'll give you a brief review in just a few minutes. But before we get started, a few things I wanted to mention to you. Number one, please make sure you do get started on assignment 3. Now, a lot of people tell me that assignment 3 is not as difficult as assignment 2. And I kind of agree with that because there's some simplifications. Number one, we are not going to be running anything with multiple cores, so multiple CPUs. So we're only going to be using a single CPU for assignment 3. Number two, assuming you have assignment 2 already implemented, assignment 3 is you're not implementing any new multiprocessing features. You are simply implementing the core map, which, while you do have to protect from multiple threads accessing at the same time, that's actually fairly trivial to do. However, debugging can be a bit of a nightmare. Not as bad as A2, I think, but it is still something to be aware of. So do make sure you get started on A3 as soon as you're actually able. And the previous episode is a bit of a guide. And of course, there are the previous terms guides online as well. And they're all labeled, so if you need to find them, it should be pretty quick. The other thing that I wanted to mention is don't forget that we actually have quizzes for each of these modules, and they are posted to Learn. And I think all of them may be posted now. I'll have to go in and check. So make sure you do them. The one thing that you don't want to do is leave them all to the last day, i.e. the day that they're due, because that's going to be A, a lot of work for you, and B, that's going to really cut into your time to study for the final online quiz. So you do have a final exam of sorts. It's going to take the form of a longer quiz on Learn, and no, everybody is not getting the same paper. There is some randomization, but to make sure it's fair, things are divided into difficulty level, and everybody gets the same number of difficult questions from each of the pools. So it's we tried to make it as fair as possible. All right. So, before we get into our review, let's look at our OS of the day. So today's OS of the day is called OS2. Now this is one I've actually featured in the little video clips at the end. This was actually featured in the GoldenEye clip. So I don't know if many of you are James Bond fans. But GoldenEye is a classic one from the 90s, and it's a lot of fun, and there was an N64 game that was made on it, which was also a lot of fun, except for Natalia. She was really annoying, because she's always telling you what to do in the game, and things like that. It's like Navi in Ocarina of Time. It's kind of annoying, or the owl. Anyways, so OS2 was actually shown in that movie where they're blowing stuff up. If you actually look at the computer screens, they're actually running OS2. So what is OS2? So this operating system was released in 1987, and it's another collaboration between Microsoft and IBM. It stands for Operating System 2. I know they're not exactly the most creative OS namers. And it was developed to be released with the PS2 computer. Now, I don't want you to confuse that with the PS2 port that mice used to use. So there was a time where they used like a mice, you used to have wires, and the first mice that I used actually had connected to your serial port, and then the PS2 port came out, which was this little round port, and it was such a pain. It looks like the S video, but it's such a pain to get the thing oriented. Now, of course, it's USB, and everybody uses wireless. Like, I don't have a wire on this one. But PS2, and we're also not talking, of course, about the PlayStation 2. PS2 is actually a desktop computer that IBM released in the mid-late 80s. So the idea behind OS2 is that it's supposed to be an upgrade to DOS. So if you remember, DOS is a really restricted operating system. It doesn't do things like differentiate between the kernel and the user program. It doesn't really do virtualization or abstraction. It's a very, very basic operating system with limited file system access, limited memory access, and so on. It doesn't have a GUI. There's no point-and-click interface. So IBM wanted something that gave you a lot of those features. So they have a DOS it is kind of like DOS with a protected mode. It offers virtualization of resources, and it actually has a desktop GUI environment, like a point-and-click environment. They decided to create their own file system, so DOS was using things like FAT16 and FAT32 in later days. But their file system is called HPFS, and it's going to support longer file names and larger files, and it's also an interchangeable file system, so it's fairly easy to switch between different file systems. They also supported multitasking and up to 64 CPUs, which, to be fair, I mean, not in the 80s, I wouldn't say it was common to have multiple CPUs, but certainly I want to say in like the late 90s. You didn't really have multi-core. That kind of came in the early 2000s, at least in consumer devices. But it certainly was, if you were a big computer enthusiast, you would buy like a super micro board that would have like 2 CPU slots on it, and you could put 2 CPUs. So that was kind of useful. The idea behind OS2 is they wanted something for consumers, but also something for commercial development as well. And to make sure places like banks and companies would actually purchase this operating system, they wanted to make sure that everything in OS2 was actually compatible with DOS and Windows. So they wanted to make sure that whatever application you had in DOS or whatever application you had in Windows, you could take it over into OS2 and it would work the same. Because if you want to convince people to switch to your operating system, you want to make sure that whatever tools they used before, they don't have to purchase new ones, number one, because that's going to be an extra expense on top of paying for licenses for your OS, but you also want to make sure that they behave the same way. And so OS2 is actually compatible with DOS and Windows applications. And it was actually competitor to Windows throughout the late 80s and the 90s. It lost. And that might be why you've never heard of it. It was quite popular with businesses, and I kind of understand that because it wasn't consumer friendly. So I've actually used OS2 a lot. My high school in the middle of nowhere had a lot of computer labs, which was really bizarre because, you know, a bunch of farmers generally aren't interested in computing, but that's just, we had a lot of computer labs. And I want to say there was maybe 2 or 3 of them that actually ran OS2. And so I spent some time in there using it. And it's actually, you know, when half your labs are using Windows 3.1 and the other half your labs are using OS2, you got a pretty good sense of the usability of the 2 different operating systems. And I can safely say that Windows 3.1 was a pleasure to use in comparison to OS2. OS2 was very tricky. It was very bizarre. It was very odd. The interface wasn't intuitive. Not that Windows 3.1 was particularly intuitive, but it was much easier, I think, for people to understand. And so in the consumer market, it kind of tanked and, yeah, it doesn't exist anymore. Now, where is OS2 kind of still possibly existing? And that's those POS devices again. So things like receipt printers and cash registers and little terminals like that. So I'll show you what OS2 looks like. So this is OS2 Warp, which I'm pretty sure is the version that I used. So, I mean, if you're looking at this, and I know that it's kind of blocky because I'm, you know, streaming at 4K and this was very much a 640 screen, 640 by 480 screen. I mean, aside from like the GeoCity style textures, you've got like command prop and overlapping windows, and it's kind of got like a start menu up in the corner. So it's actually not, like, looking back at it now, this isn't that hard. But at the time, Windows 3.1 was just more intuitive to use. And it was easier to find your programs. And the compatibility between Windows and DOS and OS2 I didn't find to be that convincing, to be honest. But yeah, this is OS2 Warp. So this is from the mid-90s, I think. All right, so there's a question on Twitch about when will we get our marks back for A2, sometime before the deadline of A3. I mean, that's always our hope. But something to keep in mind is that I know for your other CS courses, you use like Marmoset, and there's all this automatic grading, and then the TAs just look at your style. We don't do anything like that. We don't have automatic grading for our assignments. So our TAs actually have to manually grade them. So they run them several times using the tests that we provide, and then they're going to look at your results. So it does take time. Usually it's 10 days after the slip day deadline. So I think it was due last Monday. I'm hoping that you will get your grades next week. But I can't make any promises. In these current times, obviously, we're trying to be a little bit more flexible, both with you and also with our graders who may not even be in a place that has decent internet. So be patient. We will do our best to get the grades to you as soon as possible. All right. So let's do a bit of a recap of where we left off last time, which I know it's been like almost 2 weeks since we talked about any of these topics. So we were talking about devices and I/O. So this is how are we going to interact with the different input and output devices that we actually have on our computer. So that's things like the printer, your screen, keyboards, mice, the clock, your network interface. And we talked about how there's the bus, which is actually what is the kind of like the communications pathway between all of the different devices. We also talked about how each device actually has a small amount of computation power of its own on board. And as part of that, we have these things called device registers. So just to remind you, there's a status device register, which tells you something about the device, like an error code, or what am I doing right now, or what is the current time. There's command registers that you write to tell the device to do a specific task, and data registers, which can be used to transfer data to and from the device. And then you can combine these together into a status and command register where you read to get the status and you write to tell the device what to do. And we looked at how the specifications for the different device work and what kind of device registers they have and how they might be used. So we looked at the clock and the serial console, and then we talked about 2 different approaches to writing device drivers. One of them using the polling approach, where we are going to tell the device to do something, making sure we get a mutual exclusion to tell the device to do something, and then we're going to poll the device's status registers to find out when it is completed. And while this seems like a very old-fashioned idea, what's really interesting is that USB drivers are actually polling drivers because they don't send interrupts because they didn't want to corrupt the data going over the USB lines, and they didn't want to add an additional line to the USB architecture. So they actually use polling. So some of your hardware actually does use polling, but a lot of your hardware actually said, we fire interrupts. So there's no reason for you to poll. So we split the device driver into 2 parts. The first part is going to initiate contact with the device, tell it what to do. And then the handler for the device is actually going to say, when the device throws an interrupt, this is what we do to figure out what just happened and handle it. So no polling in this case. We also talked about 4 different techniques that we could transfer data to and from the device. We talked about port mapped I/O, which was a separate address space that uses fewer bytes to address things. And this required the use of special I/O instructions because, of course, it's not regular memory. And while this is faster, it's also more restrictive because there's not as many slots for devices to actually make use of. Now, something that's much more flexible because we don't need special instructions and we have a lot more memory is memory mapped I/O, where the device registers are going to map just to regions in RAM. Of course, this is a little slower because the device now has to listen to the main address line, and the main address line is super, super busy. So every device is going to have to translate every single address and then ask, is this my address? So that's a little bit slower, but it's a lot more flexible than the port mapped I/O. Now, that's really good for small transfers, but when we're looking at bigger transfers of data, like let's say we want to write to our hard drive, there are techniques for doing large data transfers. So there's program-controlled I/O, which is where we are actually having the CPU perform the transfer. So the CPU is going to be actively involved, like doing the store words to the device registers where they are mapped in memory. And that is what OS 161 does, and certainly there are devices in your system which do that. But the preferred method now for doing large transfers is direct memory access, where the CPU is going to initiate contact with the DMA controller, and then the DMA controller is going to facilitate the device going to memory directly and grabbing things for itself, so that the CPU doesn't actually have to perform that sequence of writes. So that's going to be a lot faster. But the details of how this works, we have glossed over so many details here, are quite complicated. And this is a newer technique. I mean, I say newer, but I want to say it's at least 30 years old. It's got to be at least 30 years old. All right. And then at the very end of our last real episode, we actually talked about persistent storage. And just to kind of review that, the persistent storage is any kind of storage mechanism where the data is going to be maintained after power is lost. So they say non-volatile. So things like the RAM in your computer is not persistent storage. It's actually volatile because the second your computer loses power, any data that's stored in RAM could be lost. So it's not persistent. Now, persistent storage is actually a really old thing, as we mentioned before. For example, punched metal cards for weaving looms, the jacquard loom, actually go back to the 1700s. And we actually used punched paper cards and punched paper tapes up through the 1970s. Magnetic drums were one way of doing things in the 1930s to 1960s. And magnetic tapes, that is, you have like a thin plastic tape covered in a ferromagnetic material, and we're altering the direction of the magnetic field of regions of the tape to store ones and zeros. And magnetic tapes have been around since the 1920s, but what's really interesting is we still use those today. And the reason why we use them is because a little tape about this big, it's not very big anymore. It's like when you're talking about the 70s, it's like 1-inch tapes or 2-inch tapes or things like that. But now the tapes are actually really, really small little cartridges, and they can hold terabytes of data, and they're super cheap. Now, they're not good for everyday use. This is not something you'd want CSEF servers to actually be using as like a daily storage mechanism, because obviously trying to find stuff on a magnetic tape, you're going to be looking at big O of N search time because you actually have to search the whole tape. So that's not good. But they are really good for archives because it's cheap and effective storage. And since you're not going to be searching the archive all the time, it's a great way of doing it. So magnetic tapes persist today, but typically for archival purposes. And certainly in the film industry, that's exactly how they do archives, is with magnetic tape because it is cheaper. Now, there are other forms of magnetic storage as well, which of course are floppy drives, starting with 8-inch floppy disks, which actually used to have a box of, and I don't know what happened to it. 8-inch floppies. There were these giant dinner plate size things. And then there were 5 1/4, which is what I grew up using, and then of course 3 1/2, which came in a hard case. But the technique, it's all the same thing. It's a thin plastic, flexible circle platter of plastic that's covered in a ferromagnetic material. And hard disks are kind of the extension, a little bit more durable version of that. And we'll talk more about hard disks today. And we're also going to take some time today to talk about solid state memory and ReRAM as well. Now, CDs and DVDs and Blu-rays, how do those work? So those are actually altering the optical surface of the material. And then you like shine a laser onto it, and the laser is going to like reflect off in different directions. Which is why when you have scratches on things like that, it causes, skips and the movie to not really work. It's because it's changing the data. I'm kind of glad these have all kind of gone away, to be honest. And by the way, CDs, DVDs, and Blu-rays are kind of like an extension of a record. So I don't know if any of you have ever used like a vinyl record machine. I mean, I had one when I was a kid, but it's like a hard piece of plastic. It's actually not that hard. If you put it in the sun, it'll melt. And it's got grooves etched into it. And as the needle goes over the grooves are, even though they look like they are just, little scratches, they actually are wavy, and it reproduces the sound wave, which is kind of neat. All right, so let's talk more then about hard disks. So this is where I wish I had a dead hard drive that I could actually open up and show you. Unfortunately, I don't keep my dead hard drives, and since we're not in person, I can't walk over to CSCF and say, hey, can I have one of the 8 million dead disks you have sitting in the trash bin? I probably should have done that years ago and then just kept it, but I didn't. So if you were to open up your hard drive, and please don't open up a hard drive. It's really bad. If you were to open it up, though, what you would see on the inside is a spindle, and on the spindle, you would see a bunch of what look like metallic platters, these disks. And then for each of them, now I know I've only drawn one of these arms here, these little armatures, but for each of the platters, there's going to be a separate arm. And at the end of the arm is a very, very tiny thing. You probably can't barely even see it, is a read-write head. And what happens is these platters spin, and the read-write head moves from the outside of the disk to the inside of the disk. And so when you want to find a piece of data on this, you're going to be rotating the platter around and moving the armature to the correct position, and then the read-write head can read the bits. Now, what's interesting is these platters are not made out of plastic. They're made out of glass or porcelain. Do not drop your laptop unless you have an SSD. Do not drop anything with a mechanical hard drive. It's uncommon for them to survive falls. It's not that I haven't seen them survive falls. It's that they're literally made out of breakable materials, and they can break very, very, very easily. So on top of the glass or porcelain is that ferromagnetic material where we're altering the magnetic field's orientation to store data. Okay. These are very fragile because what's really interesting, so in addition to the fact that these platters, and in disks today there's like 4 or 5 of them, in addition to them being super, super thin and made out of super fragile material, you've got this read-write head that sits over each of the platters. Now what's really interesting is to us it looks like it's touching the platter, but actually it's not touching the platter. It's sitting just a few microns, not very far above it, but not actually touching. The head does not touch the platter, and if it does touch the platter, we call it a head crash, and it can actually do physical damage to the disk, and it makes a horrible, horrible sound. And if you don't believe me, so let's open up a new window here. Okay, that's weird, but whatever. So let's do head crash sounds. So there's actually like this website. I think this is the one. This isn't the one, but what's interesting is the sound of a head crash, of course it's flash media here, is actually different for each of the different disk drives. Click of death, it's often called. And every little disk has its own. So I'm going to turn the volume up on my computer. I'm not sure if you're going to be able to hear this, but let's find out. So let's do. So that's one. And if you can't hear these funny little sounds, do let me know. I was hoping I could find a quantum fireball, to be honest, because one of the ones that was notorious was the quantum fireball. They make me giggle. So you can kind of hear those weird clicking sounds, or sometimes they're thunks. But if you Google for this, you can actually buy disk drive. Each disk drive kind of has its own unique click, which is kind of interesting. If you ever hear that sound, the click of death means your disk drive is dead, and recover all data you can while you can. All right. I don't know how to get Apple out of this weird mode here. So I'm going to close. Oh, that's cool. So I have a video I'd like to show you, and it's kind of a silly video, and please, if you're watching on Twitch, please do let me know if you can hear the audio for it. Actually, so there might be an easier way to do this. Well, let's just open it up. If you can't hear the audio for the video, do let me know, and I will tinker with it. But the video I want to show you, it's a really silly video, but it's a real video. And what it is some guys in a data center related to Sun Microsystems wanted to show you just how sensitive these mechanical drives are to things like added vibrations. They wanted to show you just how fragile they are. So I'll show you that video in just a minute. Just a question on Twitch. Does glass or porcelain have certain properties that make them a good material for this? My understanding is you want something that does not conduct, and you also want something that's pretty good with heat, because these discs do get very, very hot because they are spinning today at like 10 or 12,000 revolutions per minute, and they don't stop spinning, which is something people don't realize, is your discs are almost always spinning unless you buy the green versions. Because it's expensive to spin up and spin down all the time. So you want something that's going to be not conducting, but you also want something that's going to be able to withstand heat, because the hard drives do get very hot. So that's my understanding for that. So I'm going to load up this video now. And it's a lot of fun. And again, please let me know if you can or cannot hear this.
Measuring disk I/O operations broken down by latency. I've also drilled down to disk I/O operations taking at least 520 milliseconds broken down by disk.
Okay, so what he's got is he's in a data center, so there's a lot of white noise here, and he's got this monitoring tool. Now, the top plot and the bottom plot are not interesting. What I want you to watch is what happens to the middle plot. So the middle plot is the disk I/O operations that are taking more than 500 milliseconds. And I want you to look at the plot right now before he conducts the experiment. You'll note that almost no disk operations are taking more than 500 milliseconds. Little tiny blips here, but it's essentially empty.
Trace so I can do performance analysis of disks. I'm applying a write workload to 2 JBODs, which are over here. Blinking on these JBods because they're doing work. What I'm going to do is not recommended. This is
yeah. So what he's going to do, whatever you do, do not do this on a co-op term. It's a really good way to get fired. I mean, unless of course you want to get fired from your co-op.
Supported, do not try this at home. Ah!
Look at that. So before he screamed at it, there was almost no operations taking more than 500 milliseconds. But once he screamed at it, there's a sudden spike. And of course, you've got to repeat the experiment because once is not enough. And there's another spike corresponding to when he screamed at it. So why did this happen? Well, the truth is, his little lab there is actually quite noisy, but it's a constant white noise. So the operations are going to be slowed down a little bit from the vibrations from that sound. But when he screamed at them, he was adding a new vibration that was actually affecting the speed of the disks. That's crazy. These disks, these mechanical hard drives, are very, very sensitive. They're sensitive to vibration, drops. They're not the world's greatest disk drives. So that's a fun little experiment. Please, again, don't try that at your co-op job. You'll probably get fired for that. So, I mean, why do people use these still if they're obviously so fragile? Because it's still more cost effective than getting an SSD of the same size. So, like, you can get 12 and 16 terabyte disks, and they are still cheaper than the SSD equivalent. Some other negative issues that go with these devices. So in order to find the data, things actually have to move. And there's actually two motors in the device. So there's one motor to rotate the platters. And by the way, the platters do not move individually, nor do the read-write arms. They do not move separately. They move, if one moves, they all move to the same position. So if you were to look at how data is arranged on a disk, and this is kind of a bad example here, but it's essentially, you've got these tracks, these concentric rings, and each ring, even though each ring is technically of a different size, that each ring holds the same amount of data. That is the assumption that we make for this. So each ring has the same amount of data, and then the rings are effectively divided into a pie slice. So I'm actually going to bring out OneNote here. And I don't know where I put my, there it is. Apparently, my daughter had a fairy wand sitting on my tablet. So I'm going to bring up OneNote here because I want to draw something for you all. It'll be a little bit more accurate for what we're doing. All right, so what you've got is, here's your platter. And it's divided into these concentric rings, and there's your spindle in the middle. And then what we're going to do is we essentially, oh, wow, this is really badly drawn. We're going to cut it like a pizza. And each of these little chunks inside a track, so that there is called a sector. And we make the assumption that every track has the same capacity, every sector has the same capacity, and every track has the same number of sectors. So that is an assumption I want you to make, even though geometrically speaking that may not make a lot of sense. Please just make that assumption. So what the idea is when you want to read or write something to one of these disks, what you have to do is the platter has to rotate so the correct sector is aligned with the read-write head, and the read-write head has to move to the correct track. So there's two motors that are moving. So the interesting thing is that the platters are always spinning. Once the platter rotates to the correct sector to begin the write, it doesn't stop spinning. It's going to just keep going around and around, and so we may have to do a little more waiting before the read-write head actually moves to the correct track. The platter these days likes to spin usually at a minimum of 10,000 revolutions per minute, and the read-write head, or the seek operation where we are seeking the correct track, actually tends to be the cost that dominates. It tends to be the slowest operation. Now, admittedly, when I was younger, we were looking at disks that had like 5,400 RPM, and they were much, much slower, but the seek was also slower. And again, what I want to say is the platters do not move independently, nor do the read-write arms. You can't perform a read or write on multiple platters at the same time. It's not to say you couldn't design one that doesn't do that. It's just to say that they don't right now. Okay. So here you've got this exceptionally fragile device made out of glass and porcelain, and it's spinning at a really high rate, so it's going to use a lot of power. And because it is using a lot of power and it's spinning at a high rate, and there's two motor arms that are moving, it's going to use a lot of electricity, generate a lot of heat. So these devices, mechanical hard drives, they are heavy. They're actually quite heavy. Compared to their SSD counterparts. They have moving parts that are made of very fragile materials that should never touch. And they use a lot more energy because they are constantly moving, and they generate a lot of heat because of this. Which is why a lot of these things actually have separate coolers for the disk drive compartment. So one of the many reasons why these are kind of outdated tech. But let's now look at the costs. So let's suppose you wanted to do an I/O operation on one of these disks. How much time does that take? What is the cost of an I/O operation on a disk? Well, the cost is the sum of three things. The first cost is the seek time. So the seek time is how long it takes to move the read-write head to the correct track. So move to the correct track. This is typically the dominating cost, as we'll talk about more. And the maximum seek time is going to be the time it takes to go from the innermost track to the outermost track, because that is the maximum seek distance. And the minimum, of course, is 0 if you are already on the correct track, which is highly desirable behavior, because this is usually the dominating cost. You add that to the rotational latency. Remember, I said the platters are always spinning. They never stop. Because if they did stop, then you could do these two operations at the same time, and then you wouldn't have to add them together. You would just take the maximum of the two operations. But the platters don't stop when they arrive at the correct sector. The platters just keep spinning. So we add the seek time to the rotational latency. And the rotational latency is how long does it take after the seek has happened for the platters to spin to the correct position. So it really depends on the rotational speed of the disk, and the minimum could be 0 by fluke. You might be over the correct sector, and it could be up to the cost of a full rotation. And then once you have the disk at the correct start position, then you can actually perform the read or write. Now, the read-write head doesn't read a whole sector. It reads one bit at a time, which means there is a transfer time. Once the read-write head is in the right position, there's a time it takes to actually transfer the data. It is read or move through all the bits of the sector. So the transfer time is how long does it take for the platter to rotate through the sectors that you are reading. And that is typically going to be a fraction of the rotational speed related to the proportion of the track that you are reading. So if you are reading half the sectors on a track, then the transfer time is going to be 1/2 of the maximum rotational latency. If you are reading 1/10 of the sectors on the track, then you're going to have a transfer time 1/10 of the maximum rotational latency. So it's a fraction of that. And so the request service time, or the IO request service time, is the seek plus the rotational latency plus the transfer time. Okay, so there's a question on Twitch. What if the read-write takes longer than the time the sector rotates past, or does that not happen? So that's actually going to be part of the disk's design. So if the platter moves faster than the read-write could happen, that doesn't make sense because you can't slow the platter down. And you don't want to have to wait for it to rotate around again to get the next bit. So the speed of how the disk can read-write is going to be carefully set such that the platters are not rotating at a rate that is faster than the speed that you can read-write, because it doesn't make sense. It's not to say they've never made a disk that did that. It's just to say that from a manufacturing perspective does not make sense. All right. So there's a bunch of formulas that we can use to actually compute these different things. So we have a little example here, and I'll go through it rather quickly. So we have a disk that has a total capacity of 2 to the power of 32 bytes. Now, something I want to tell you is that on a disk, you do not do bit-based addressing, and you don't do byte-based addressing. Disks are addressed by sector. So if you want to read or write a byte in the middle of a sector to a disk, you can't do it. You actually have to read the whole sector or write the whole sector. So we do sector-based addressing on disks, not byte-based addressing. But let's suppose that your disk has the power of 2 to the 32 bytes. So it's a 4 gigabyte disk, and there's one platter, and the one platter has 2 to the power of 20 tracks. Each track, has 2 to the power of 8 sectors, and the disk operates at a speed of 10,000 RPMs. There is a maximum seek time of 20 milliseconds. So we want to now know some information about the disk. And this is the kind of question that you can anticipate shows up on the final quiz. So how many bytes are in a track? So if you want to know how many bytes are in a track, you take the capacity of the disk and you divide it by the number of tracks. Now this particular formula is going to work for a single platter. And I have the more general formulas for multi-platter, multi-sided disks actually posted to Piazza in that extra sample problem thread. Okay, so bytes per track for this disk is the capacity divided by the number of tracks. If I want to know how many bytes are in a sector, then I take the bytes per track and I divide it by the number of sectors per track. To figure out the maximum rotational latency, which is how long does it take to rotate the platter exactly once, you do a little bit of cross multiplication and you find that 60 divided by the revolutions per minute is going to give you the maximum rotational latency. Now, if we wanted to know the exact cost of a request service time, then we would need to know what track are we on and what track are we going to, what sector are we on and what sector are we waiting for. We often don't present that information, and so we don't know exactly how long each of those operations is going to take. When you don't know what track you're moving from and to, we use the average seek time. When you don't know where the platter is and where it has to go to, we use the average rotational latency. And we no longer do the derivations of these in this class, but the average seek time is the max seek over 2, and the average latency is the max latency over 2. So these are formulas that you should memorize. The cost to transfer one sector, so this is the transfer time for one sector, is going to be the maximum rotational latency divided by the number of sectors per track. If we were then saying, well, what's the cost to transfer 2 sectors, then it would be 2 times the sector latency. And then to get the expected cost to read 10 consecutive sectors, it would be the sum of the seek plus the rotational latency plus the transfer time, where we're multiplying the sector latency by 10. Okay. So let's actually calculate these out. The answers are on the next slide. I'm not going to go through them, but you can see here just basic examples. And what we end up with in the end is that this disk I/O takes about 13.2 milliseconds to complete. Now, what's interesting is if you are reading from disk, and let's say you're reading like file data from disk, that means your program is going to be idle for a minimum of 13.2 milliseconds because you have to wait for the read to complete before you can move on. Disk I/O is very, very expensive. Very expensive. Now, if we look at these numbers, what we can see is because the disk is always spinning, it's much, and the seek time is the dominating cost typically, it's much more efficient to do a large transfer than a bunch of small ones. So let's say you wanted to read a movie from your disk. So I don't know how big the movie files are that you have, but some of the ones I have are in like the 40 gigabyte range. And if you have to ask yourself, which is more efficient? Reading the movie if it was on one single track, the whole movie, 40 gigabytes on one track. Is that faster or slower than reading 40 gigabytes where the data is spread across sectors from all tracks? And the answer should be fairly obvious. A long read, a long transfer from the same track is much faster, because you only have to do one seek operation. The problem with doing a bunch of smaller little reads is that for each of those sector reads on different tracks, you have to do a new seek. It's almost like a brand new I/O time. So we have a preference on disk drives to do sequential I/O rather than random I/O. Random I/O is very, very bad for disk drives. And I'm not sure if you've ever seen Windows Defrag. I suppose I could probably bring it up here in a new window. So let's do Windows Defrag. So Defrag was a tool, and I mean it still exists, but I kind of want to find the Windows 95 one, because that's what I'm used to using. But let's just use this nice picture here. I don't want that. Just show me the picture. It's not gonna. All right, so what you can kind of see here, and I know it's really small, is a bunch of little blocks, and some of them are red and some of them are blue, and they're scattered all over the disk. So what happens is your files are not stored contiguously on your disk as much as we wish they were. They're not stored contiguously on a disk for the same reason that we don't use segmentation as virtual memory. You end up with external fragmentation. So what we kind of do to store files, as we're going to see in the next module, is we do something kind of like paging. And we divide the file into a bunch of blocks, and then we scatter the blocks across the disk to reduce the amount of external fragmentation. The problem is, now you have this fragmented disk where the files are broken up, and they are not sequential, which means we are doing more random I/O than sequential I/O. And in the 90s, this was a really big deal because the disks weren't that fast and your computer wasn't that fast. And so when your disk became fragmented due to the files being scattered randomly all over the disk, your computer got noticeably slow. And so you would have to run defrag almost every other day, depending on how heavy of a user you were. To what Windows defrag does is it looks at each file as, you know, and it finds all of the scattered blocks and it tries to rearrange the file such that the file is contiguous on the disk. So you go from this kind of scattered randomness, and what you want to go to is something that looks more like this here, and this is from Windows 98. So you want things to be, okay, here's all the contiguous file data allocated in the top and all of the empty spaces at the bottom. So the defrag tool, its goal is to take the randomness of how your file is scattered across the disk to make it as contiguous as possible, because sequential I/O is going to be faster than random I/O on these devices. True story, I don't know many people that run defrag anymore. I mean, so number one, please do not run defrag on an SSD. That's very, very bad. Very bad. But even on a mechanical hard drive, I can't think of the last time I ever ran defrag. Like, I honestly think it was like the early 2000s was the last time I ran defrag. It's not as big of a deal anymore as it used to be. Okay. Is there anything else that we could do to reduce the average seek time? So it's obvious to us that sequential I/O is going to be faster than random I/O because it's minimizing seek time. But is there anything else we could do to minimize seek time? There is. It's called disk head scheduling. Now, disk head scheduling can happen on the disk itself. The disk may have its own scheduler. It can happen in the operating system, so in the kernel. It can also happen in both places. So the OS may do its own scheduling, and then the disk drive may do scheduling on top of that. What does disk head scheduling mean? So I/O operations, you can only do one at a time. So you have a queue or a pool of I/O requests. And so the goal here is we want to service those I/O requests in such a way that we are minimizing the average seek time. So how could we schedule these? Well, you could use first come, first served, right? The nice thing about that is that nobody is going to starve. Starvation is going to be an issue here. So the idea is if this little black square represents the current position of your read-write head and these concentric rings are your tracks, at the very bottom, which you may not be able to read, so you'll have to open it up on the slides, is the arrival order of the jobs. First come, first serve, you serve the jobs in the order they arrive. And you can see with these black arrows here just how much head movement we're doing. We didn't minimize anything, but it was really fair because we did things in order. Now, the other thing to keep in mind is that jobs are constantly arriving. Like, it's not like, here's my jobs, no more jobs come. Jobs arrive all the time because we use on-demand paging, because we're reading and writing files. So this queue is constantly changing. So first come, first serve guarantees that no jobs starve, but we haven't improved anything. What if we did a greedy approach? So we did shortest seek time first. Okay, that's actually a really interesting idea. And it does actually minimize the head travel. So we start at 53, track 53. And of the jobs I have right now, I see the closest to 53 is 65. So I do 65. And then the closest to 65 is 70. So I do 70. And then I do 37. And then I do 14. And then I come back and I do, what's this one here? 104. And then 122. And then 130. And then 183. I minimize the seek time. Look at the difference. That's all the head movement from first come, first served. And look at how reduced it is here with shortest seek time first. But there's a problem. The greedy approach does minimize it, but there's a big, big, big problem. What if the jobs that are continuously arriving are all near the head? Then those jobs that exist out at the furthest distance away from the head are going to have to wait and wait and wait. And there's the potential that they starve. So shortest seek time first is nice in the sense that we're really minimizing that seek time, the average seek time, but it's not nice in the sense that we get starvation. That's a worse problem. That's you open a movie in VLC and nothing happens, and then you chuck your computer out the window because you get frustrated. I hate waiting. So there's an algorithm we can use that actually, it's going to give us better than average seek time than first come, first served. Not probably as good as shortest seek time first, but it's going to guarantee we don't starve, and it's called the elevator algorithm. So the idea is your head is in a particular position right now. We are going to choose a direction to move. Let's say we choose this direction to move. And what we are going to do is we are going to travel in this direction only, and we are going to service every job that we see along the way. So in the case of this one, we start at 53, and we've chosen to go to the outer track. So I do 53, 65, 70, 104, 122, 130, 183. I get to the edge of the disk. I see there's no more jobs in front of me. So I turn around, and I go back the other way. And I service 37 and 14. I get to 14 and there's no more jobs in front of me, so I turn around and I go back this way. So you'll see that we're not constantly going back and forth. We're sweeping all the way to the end of the disk and then all the way to the end of the disk. So that's nice. We are getting a little bit better seek time, and we avoid starvation because even after we've turned around and gone this way, if a job arrives right behind me, I know once I get to the edge of the disk that I'm going to turn around and come back, and I will get to the edge of the disk, and I am going to turn around and come back and service everything else. So this is also known as scan, which is what your disks do today. This is very common, and there's lots of different variations of it, but this is one of the disk head scheduling algorithms that are used on many common disks. So that's kind of cool, right? But how do we write the device driver for this sucker? Okay, actually, it's not that bad. So first off, this is the sys161 disk controller, which is what's going to control the drive. So it doesn't have that many registers. It's got a status register that is the number of sectors on the disk. It has a status and command register called status, which is a really bad name, obviously. Let me just... I don't remember what that status register's for, and of course I haven't written it down, because oops. And then we have a command register, and when we write to the command register that is the sector number, we're telling the disk which sector we want to read or write. And if we write a read to the command register here, then that would tell us read from sector X. And if we put write here, it would be write to sector X. We have a status register for the rotational speed, which can be useful for estimating the cost of how far along you are. And then we have a 512-byte transfer buffer where we put our data to be written to the disk, or the disk will put the data to be read from it. So that is our specifications. Now, what does the driver and handler look like? Okay, so first off, we have two semaphores now. One is a binary semaphore to make sure that only one disk I/O operation is happening at a time, so we have mutual exclusion on the disk. So that is the disk semaphore. So once we have mutual exclusion on the disk, this is for writing to the disk, by the way, we are going to put the data that we want to put onto the disk into the device transfer buffer. So 512 bytes. Remember, you have to do sector reads and sector writes. You can't do partial sector or read or write. So we have to write the whole sector. So we put the data into the transfer buffer, and then we're going to write the target sector to the sector number register. So that's this one right here. And then into that command register, we put the write command. And when we do that, it initiates the write of the data in the transfer buffer to that sector on the disk. Now, of course, the disk is going to have to move to the correct position first, and then it will write the data. Now we have this P disk completion semaphore, and I can tell you that this semaphore's initial value is 0. So we need to wait for the operation to complete. If you're thinking about a piece of code that you have written, typically when you're dealing with disk I/O, you don't want your program to continue until the disk I/O has completed. So you need to force the calling program to wait for completion, and that's what this does. Now, for write, usually you can go ahead, except if you're doing another write where you'd end up waiting here. But sometimes you also want to check, did the write succeed? Was there an error code? Maybe that was a bad sector number. Maybe the sector is bad because some of the sectors on your disk might actually be bad and you might not be able to write to them. So, interesting problems. So we need to wait for the disk to complete the task before we move on. In the interrupt handler then, we acknowledge completion once the disk has said I'm done, and then we V the completion semaphore. Now what's interesting here is by Ving the completion semaphore, the thread that handles this is almost never the thread that did this. But because we are actually going to sleep here, we're saying this thread, the calling thread, has to wait for the disk to finish, which means another thread is going to handle this. And in order to return to the thread that initiated contact to the device, you need to V the disk completion semaphore, which will wake this thread up. It can handle error codes or do whatever, and then release a hold of the disk. For the write handler, this doesn't always make sense, but when you look at what read does, having that second semaphore does start to make sense. So again, only one disk I/O operation at a time, so we P the disk semaphore. We're going to write the target sector number, and then we write read to the status register to say, read data from this sector for me. And then we wait for that to complete. Because if we are reading from the disk in a program, we need to wait for the data to be in the in our data structure before we move on. So we need to go to sleep to wait for it to complete. Another thread handles the interrupt, acknowledges completion to the device, and then wakes us back up. When we wake up, we need to copy the data from the device transfer register, the buffer, to our address space. Now, we could have the thread that handles the interrupt do it down here, but that doesn't make sense because that thread might belong to a different process. And why would you have a thread from a different process copy data to you? That's silly. So it makes much more sense to have the thread that wanted the data perform the transfer. So this second semaphore allows us to transfer control back to this thread here, copy the data into our address space, and then release the hold on the disk. And we can handle error codes and so on. Now, does every device driver and handler need to use two semaphores? No, things like the clock device didn't need it because it didn't matter who handled the interrupt. If, however, you have a device where it does matter, we need the caller thread to wait for that operation to complete before moving on, then using the two semaphore approach makes a lot of sense. Again, it really depends on what we're doing. All right. So something else I want to talk about then is how do SSDs work? We've spent all of this time talking about how mechanical hard drives work. How does the SSD work? Actually, they're very interesting. If you open up an SSD, and I don't recommend you do it, but it's certainly a lot safer than opening up a hard drive. Inside of an SSD, it just looks like a board with a bunch of chips on it. There's no mechanical parts, there's no motors, so automatically you know it's less fragile, uses less energy, and produces less heat because it doesn't have physical moving parts. And the difference between an SSD and RAM is that the SSD is capable of maintaining a charge, so it's capable of storing the memory, the values that you store. And there's been a variety of implementations over the years. DRAM was an old one, and what happened was it has transistors in the memory, and there was a battery on board so that when your computer wasn't on, and receiving power, the transistors, which are like teeny batteries that hold a small amount of charge, the battery on board would refresh the transistors so that the transistors could keep power flowing to the circuitry so that we would actually be able to keep the data. Now, we don't tend to use this tech anymore. What happens if the battery dies? Oops, there goes all your data. Not such a good idea. What we use now is called flash memory. Flash memory, also known as NAND flash memory because it uses NAND gates, traps electrons in a quantum cage. My understanding is this technique can still lose its charge after about 10 years of not being plugged in. But if you have an SSD that you haven't plugged in 10 years, you probably want to throw it out anyways because it was 10 years old. Just saying. Now, since there's no mechanical moving parts, we don't have to divide things into tracks and sectors, but we do divide things logically into blocks and pages. So pages tend to be 2, 4, or 8 kilobytes. Some devices have varying page sizes. My first SSD, I actually had to set it up with a page size. Page size is typically going to be set to the same page size that you use for virtual memory. For on-demand paging, so that each time you have to load a page of the address space, it's one I/O request, right? That's useful. And then the pages are grouped into blocks, which could be 32 kilobytes or greater. When I wrote these slides, it was about 4 megabytes, the maximum size. That's obviously gone up. Now, like you do reads and writes at a sector level on a mechanical drive, we do reads and writes at a page level on an SSD. And what's really interesting is we always think of an empty page as being zeros, but on an SSD, empty is 1. So question on Twitch is, what is a quantum cage? I'm not an engineer. I have no idea what that means. I'm sorry. I read briefly about it, but it was like, don't worry. I'm not going to ask you what that means. You're welcome to read about it, of course, on your own, and I can provide a link if that would be helpful. So yeah, on an SSD, 1 it means empty and a 0 means occupied. So what's interesting is that in order to, and the reason for this is it doesn't require a lot of voltage to go from a 1 to a 0. So it's easier to go 1 to 0 than 0 to 1. In order to go from 0 to 1, you actually have to apply a really high voltage. But you can't apply a high voltage at a page level. So you can, if you're writing to a new page that's never been used, you can do that. But if you want to overwrite a page that already had been written to, you can't do that. So if you want to overwrite or delete a page, you actually have to do that at a block level because you can only apply the high voltage at a block level. And so there's algorithms that are used on SSDs for overwriting and deleting flash memory. There's the naive solution, which is slow, obviously. And what it does is, in order to do the overwrite, you copy the whole block into memory. So instead of copying 4 kilobytes, you're copying like megabytes of data into RAM. You reinitialize the block on the SSD. So to apply the high voltage, convert it all back to ones. And then you're going to take the write that you wanted to do and overwrite the whole block back on the SSD. So this is going to be transferring data to RAM, doing some stuff on the SSD, and then transferring data back to the SSD. To improve the speed, your SSD controller has a faster technique for this. The SSD controller does this little trick. It says, I don't want to overwrite anything unless I have to. So if I see you're updating a file and you're updating some data on this page, what I'm going to do is I'm going to say, okay, this file no longer uses this page. I'm going to find a page that's never been written to, and that's going to be the new page for the file. So we're just going to say, okay, we'll just overwrite, we'll write to a new page. We're trying to avoid having to do the naive solution. So we keep this table, a translation table, in the SSD controller to keep track of which pages haven't been used and which pages have been. So whenever we want to overwrite something, we just tell the file to use some different pages, so we don't have to do that block. And then periodically we have to do garbage collection, i.e. trim, to actually, clean up the disk when we run out of pages that are clean. Now, what's interesting, when your SSD controller dies, so does your SSD. So one of the interesting things is that a mechanical hard drive, you can recover the data almost always, even when it dies. It costs money, but you can usually recover it. When an SSD dies, it's almost impossible to recover data. Now, a couple other things. What's really interesting about an SSD is that, and yes, the question on Twitch, in a naive solution, we are reading from the SSD and then writing back to the SSD. Yes, that's right. And in between that, we're applying the high voltage to reset the block on the SSD. What's really interesting about an SSD is that it can only be written to a certain number of times. So you can only apply that high voltage to the SSD so many times. It can't be applied because you won't actually be able to flip the bits on it anymore. And you might be thinking it's millions or billions of times. Each page on an SSD, each block, can actually usually only be overwritten about 100,000 times. Yeah, it's not that many. So in order to keep the SSD, and what happens usually is when it reaches its limit, that block becomes read-only. And then when a certain percentage of the blocks on your disk are read-only, the whole disk gets marked as read-only. And depending on whether you have a crappy SSD or a good SSD controller, it can be a really small percentage that causes that or a really high percentage that causes that. So in order to reduce the chances of this happening, what ends up going on is that the SSD does this thing called wear leveling. And then what it does is it does not prefer sequential I/O. It is actually going to scatter your file across the disk because it wants to make sure that the writes are all happening roughly at the same level on all of the different blocks. So we want to make sure that the disk wears down more uniformly, which is why you should never do defrag on an SSD. The randomness is better, and there's not really a performance hit for it. All right, so I'm going to leave that there, and I'll talk about RAM very briefly at the end of next class, but really it's just RAM that has power. But it's kind of related to our next topic, which is how files are stored. So I will talk about that in our next episode. So we will see you on is today Tuesday? I think so. We'll see you on Thursday then. So have a good Wednesday, I guess, and rest of today.